The next idea is called electric flux. Electric flux is the total number of electric lines passing through an area. Passing through an area normally. That is electric flux. Is the number of lines that pass, lines of force that pass through an area normally. It is a scalar quantity. It doesn't have any direction. Now let's look at a planar area like this. So the area of this is given by, let's say, delta S. So this is a planar surface area. Now there is an electric field acting on this like this. So it is placed in an electric field. Then there is also a normal to this surface. So the normal, if I draw a normal to this surface, that is also in this direction, that is n cap. That means the normal and the electric field, they are in the same direction, that they don't make an angle. So theta equals 0 degree. So in this case, the electric flux, we are going to write electric flux like this. Okay, so phi E, it is given by the charge, the electric field multiplied by area. Now what happens if instead of the electric field and the normal vector being in the same direction, now let's say the electric field is in a different direction. So this is another planar surface, area is delta S. Now let me see, this is the area we have. Now this is placed in an electric field which is acting in this direction, that is E cap. However, our normal vector is in this direction, n cap. Now this electric field is making an angle of theta with this normal. So I can take the horizontal component of that, which is E cos theta. So in this case, the electric flux is given by E into cos theta into delta S. So this, if I could represent that as a vector form, it is E vector dot delta S vector. Now this is a dot product. So we are speaking about two vector quantities, but we are doing a dot product of the two vector quantities, which will result in a scalar quantity. Now in the previous case, both the cases, we assumed that the electric field is uniform, but it might not be uniform all the time, right? So now we are speaking about a non-uniform field. Now let's assume an area like this. There is a small piece of area I'm taking. So this is ds1, this is ds2. Two different places we are taking. The E or the electric field is E1 here. In this case, it is E2. E1 vector, E2 vector. So at two different places, the electric field acting is two different things. So that's the difference. Now I'm drawing a normal to this surface. Let's say the normal to the surface is n. To the surface, like the normal is drawn towards us, perpendicular. Okay, it is making an angle theta. This Now let's say the normal to this is also making an angle theta with this. Now in this case the electric flux phi is given by E1 into delta S1 vector plus E2 into delta S2 vector, and we go on up to En dot delta Sn vector. We do this. Now if we express this as a summation, it is summation I is equal to 1 to n Ei vector dot delta Si vector. Now the same thing we could express that if n tends to infinity and then delta S tends to 0. Right? That means we have innumerable pieces like what we have shown. We have shown two different pieces here. Instead of that, we have innumerable pieces. That's why we have n number of pieces like that, which is infinite. And then each of these pieces is so small. Then we look at it like a very big continuous surface. Then we look at it as a very big continuous surface. Right? So if that is the case, then what happens to I is equal to 1 goes up to n Ei vector dot vector. So this is represented as surface integral. So integral, we mark this circle word, is a surface integral E vector dot ds vector. So if you are not already aware, this is surface integral. There is a reason for using a surface integral. It helps calculate the total effect of a function over a surface. So there is a function. So in this case, the function we are speaking about is E vector dot ds vector. This is a function we are speaking about, and that we are calculating over a surface. For that we use surface integral. Now let's go back to electric flux. I already told you electric flux is scalar. Now let's speak about the unit of electric flux. So electric flux I wrote as E dot E is Newton per Coulomb and ds is meter square. So the unit for electric flux is Newton meter square per Coulomb. E has another unit which is volt per meter. Now if you do that, then volt per meter into meter square, we get voltmeter. So that is also a unit of electric flux. The two units of electric flux are Newton meter square per Coulomb. The other one is voltmeter. Now we have one of the most important ideas. One of the most important ideas in the chapter on electric charges and fields. That is Gauss theorem. Now, what does the Gauss theorem say? The total flux through a closed surface. The total flux that goes through a closed surface is 1 by epsilon naught times the net charge enclosed by the closed surface. That is Gauss theorem. So the total flux, I am writing it like this. It is equal to 1 by epsilon times the net charge which is enclosed in the total surface. But we already saw that the total flux is surface integral over E vector dot ds vector. Now to visually see this, there is a charge Q. This charge indeed is enclosed inside a surface. So this is a surface. Yes. Now this surface is Gaussian surface. Now what is a Gaussian surface? It is not a real surface. There is an imaginary surface. It is an imaginary closed space which is used in Gauss law to calculate the electric field, which is used to calculate electric field due to a given charge distribution. That is Gaussian surface. Now we have a charge that is real, but the surface which we have given here, that is not real. That is not real surface. That is an imaginary surface. Now let's say our electric field is acting in this direction. So I'll write it as E vector. Then there is a small area. So this area as a vector, right? So that is ds vector. I am assuming the radius of the Gaussian surface is r. Now what we can say is the electric field at any point on S. The electric field on any point on S is given by E equals 1 by 4 pi epsilon naught into Q by R square. If E is pointing outwards, we saw that, and parallel to area vector at all the points, if it is parallel to the area vector, then theta becomes 0 degree. In that case, flux, let me write it like this, for a small portion is, that is the electric field multiplied by the small. So let's consider this small portion, and the small portion area is ds. The flux which is passing through that small portion is the electric field multiplied by the area of the small portion. Now that is E vector dot ds cos theta. But we already saw that cos theta is equal to 0, that is cos 0, which is 1. So E into ds. Now this is for that small area. This is for the small area. Now I'm going to find this for the entire area on the sphere. So that would give me the total flux. Total flux is surface integral OS over this one, we do a surface integral over the small flux, which gives me surface integral over E into ds. So I take E common, E out, so I have ds. So E is something we already know, which is 1 by 4 pi epsilon naught into Q by R square. And then ds, when I do that, it gives me the surface area of the sphere, which is 4 pi R square. Now when I combine these two, when you bring these two together, you'll be left with only 1 by epsilon naught into Q, which is nothing but our Gauss theorem. Which is nothing but our Gauss theorem.